Hello, everyone. Let's discuss training models. Specifically, we want to discuss linear regression in this section. So in this training models module, we want to discuss a couple of things, including linear regression, gradient descent, polynomial regression, regularized linear regression, and logistic regression. So regularized linear regression is closely related to linear regression. And if you recall, with regularized model, you usually tends to um, um, avoids overfitting situation. And then logistic regression is a natural extension of linear regression. So let's look at linear regression. Specifically, a linear model makes a prediction by simply computing a weighted sum of the input features plus a constant called the bias term, also called the intercept term. So if you look at this equation, you can y estimate equal to theta 0 plus theta 1 x1 plus theta 2 x2 all the way to theta n xn. And then this theta 0 is called bias term or intercept term. And then theta 1's weighted sum, theta 1 x1, etc. are the weighted sum of the input features. So in this equation, y estimate is a predicted value and is the number of features, xi is as feature value, and theta j is the j's model parameter, including the theta 0 to be the intercept term. So this model, you could use what's on the bottom right hand side using the vectorized form to represent, which would be theta dot product x equal to y hat, which is a y estimate. The question is, how can we come back with an estimate of the theta? So the way that you want to do is you use your training set X to find the set of data that can minimize mean squared error. Mean squared error is MSE here. It's a cost function for a linear regression model. It is 1 over m observations from 1 all the way to the m. Each one of them, you use theta transpose times xi minus yi. So essentially, theta transpose xi is the predicted value y hat for the s observation, and the yi is the i's actual observation of the y. We want to minimize the distance between the predicted value and the actual observed y value squared, and get the mean of all of those quantities. So this graph actually gives you a better illustration of that mean squared error. So essentially what we're trying to do is we use our linear regression line to have an estimate for this specific x, and then it's going to be there. And then for this level of x, the actual y observation is really here, and the distance would be the difference there, distance squared, summation of all of the distance squared, and use 1 over m to calculate the mean squared error. And then you trying to minimize this quantity to solve for theta. There is another way. You could leverage optimization theory, and you will be able to find the closed form solution for the theta. And then theta estimate is x transpose x inverse times x transpose times y. So this theta estimate you can see here is a value of the theta that minimizes the cost function that we just defined earlier, and y is a vector of the target value containing all the y's. So this would be your estimated theta. This theta is able to minimize MSE, which is your objective function for linear regression. And here shows you that how you can leverage Python to calculate the theta. So what you do is you add, first of all, you have a bunch of x and y's, and then they are randomly generated, and then you come back with set of x0 being 1, so that you are able to construct your x, which is really for the purpose of that intercept estimation. And then this theta best comes back using this equation, which is xb xb dot transpose dot xb, which essentially here x transpose times x inverse, and then you do the inverse on top of that, and then dot product of xb, and then dot y. So with this, you get your theta best. In this estimation, you can see that your theta best is 4.21 being the intercept and 2.77 being the slope. So once you have that, you could make predictions using theta. For a specific set of theta best, you have a specific x new underscore b you want to predict, and then this is your predicted value for the specific x new b, and then predicted y would be, for this case, you actually have two values. X new b has 0 and 2, and then predicted value would be 4.22 and 9.76 respectively. And you would be able to plot the model's predictions. These are the original scatter plots of what you have observed. You want to build a relationship between y and x1, and then the red line, red solid line, would be our predictions. Essentially, your intercept would be somewhere here, 4.12 or 13 something, and then the slope is 2.7 something. That is your best estimate of the intercept and the slope, because an intercept and a slope would define that linear line. Here is a implementation of what we just discussed in scikit-learn. It's actually rather simple. You can just leverage linear regression function, which is a linear regression class coming from scikit-learn. Once you have this class, you can fit x and y, and then once you fit, you could access an intercept and coefficient. Intercept is 4.22 as we just discussed, and then the coefficient turns out to be, which is the intercept, which is the slope, turns out to be 2.77. And then for the new observations, you would be able to predict the corresponding values. And then the linear regression class is also based on SciPy's linear algebra's LST square least square function, which stands for least square. You could call directly, and then that way you could, what you would come back would be linear algebra dot least square of x, y, and this really gives you conditions to define the convergence. And now you come back with the estimate as well. Another way to look at this is something called pseudo inverse. So pseudo inverse is really still based on this idea. Theta estimate is x transpose times x inverse times x transpose times y, and then if we group all of those three terms together, we call it x plus. So theta estimate equal to x plus times y. And then you could use linear algebra pseudo inverse of x dot product of y to have your estimated theta. The pseudo inverse itself is computed using a standard matrix factorization techniques called singular value decomposition. It's also called SVD, that can decompose the training set matrix X into the matrix multiplication of three matrices: U, theta, and V transpose. This can, if you're interested in, you can take a look at this linear algebra .svd function in scikit-learn. It's actually also, in terms of theory, it's also coming from linear algebra. Okay, so here I'll just conclude linear regression here. Basically, what you have learned so far on linear regression include two major things. I would say three major things. One is what's the objective function for linear regression. Two, what is the normal equation. Three, how can you leverage SVD to calculate the estimated theta. Thank you.